Hi, this is Chad Walber with PCB Piezotronics, and I'm about to discuss with you the very basics of performing sound power measurements. Just to give you a little background on myself, this is all of my basic information. I've got about 10 years of expertise doing dynamics testing, instrumentation setup, field testing, acoustics measurements, calibrating. I've been working for PCB Piezotronics at this point about 3 years. I have a PhD in mechanical engineering, and I am currently sit on a couple of standards committees, the IAC Electroacoustics Committee and Microphones, and I'm also the chair of the ASA Standards Committee on microphones. And I have a couple papers down here below if you want to peruse and look at those later. You should be coming to me from a part 1, which is a basics of acoustics, definitions. That's a part of this sound power basics presentation. The start of this was just to outline, this is what you need to know. This is the second part where I go to, what do you do? How do you do this measurement? And right now, that's the question. Why do we measure sound power? And there's 3 basic reasons. The first one is product optimization. To make appliances, motor vehicles, any type of apparatus you can imagine that has a certain level of sound output as a secondary effect, usually, we want to optimize it. We want to make it better. And it could be to make it louder, actually. If you look at speaker design, you may want to increase the sound power output due to of a speaker. Or in other cases, like kitchen appliances, like dishwashers, you've got a hand blender in the side there. You may want to decrease the sound power output of a particular device. Another big reason is legal or occupational health. If you're continuously working with a particular machine, or if you have people who work for you who are working with this machine, you may have to verify the sound power of the machine after it's been installed, and then verify it every year to make sure that it's not exceeding a certain limit that is imposed on you by either the Occupational Standards Committee or even an employer or the government. And government directives, that's the last point. Government directives, especially in Europe, have a requirement that all the products that could output sound power actually are rated on a yearly basis, and that any new models have to have less of an output. Snowmobiles is a very common one with this. They actually have to decrease with each new model what the sound power output is of the particular model. And there's a whole list of standards that go along with that as well. And we're going to talk about a couple of them here. So one of the questions you might have now is, who measures sound power? And the interesting thing is, you can hire somebody to do this. Various laboratories around the world, you could send your equipment to them, and they'll take the measurements on whatever device you have and report the sound power. Consultants will come on site for you if you have the equipment in an in situ measurement that you can't move. They'll come on site and perform the sound power measurement on stuff like a stamping machine or forges or anything that's too big to move, or something that, again, as I said, you would have to do an in situ measurement on. And actually, many manufacturers around the world perform sound power measurements on office equipment, computers, which you would think computers, well, they're pretty quiet already, but you still, once you have a large group of computers, that becomes additive. It's just like everything else. It's superposition of sound. And as you increase the number of sources, the overall sound power level increases of the sum of the sources. Automobiles and components, yard equipment, so lawnmowers, tractors, weed whackers, they're all on the list of things that are tested for sound power. Appliances, washing machines, as you see up on the screen here, but also dishwashers, HVAC systems. Everyone hears the furnace kick on. Everyone hears the air conditioner kick on in the summer. All those things make noise, and especially when you get to large complexes, that noise may actually affect other things. And power tools. You see a grinder in the image down and to the right here. But drills, saws, anything you can imagine that can be used on a construction site as a power tool will have sound power measurements performed upon it. So on this slide you see the three equations that are used in regards to calculating sound power from the various measurements we would actually take. The first two equations here, you see sound pressure is the very first variable. And in the last equation here, you see sound intensity, which sound intensity is actually directly derived from sound pressure, both between the sound pressure and the particle velocity, which is derived from sound pressure. So no matter what you're doing, whichever one of these equations you're looking at a sound pressure measurement with a microphone. The first equation is when it was the one you would use within an anechoic room, which the other variables in here are the distance from the source and not only the distance. Well, this is a reference distance of 1 meter, and the rest of the variables here are the atmospheric parameters. So the change in the atmosphere we talked about earlier, you see C right there, the speed of sound. You have to calculate it and make sure based on what your environmental parameters are. So that's built into this equation as well. If you look at the second equation, it looks more simple, but there's a lot hidden inside the last variable here, the C parameter. A lot of the variables that you see up here are buried in C, and we'll talk about those a little bit in the K1 and the K2 factors later on. But then the surface area over which you take the measurements, that's where this comes in. Where this one up here, you're taking a hemisphere where all the microphones are the same distance from the source. Here, you've got a surface area that you're taking into account. And interestingly enough, the surface area you're taking into account is the room surface area. So that's what you're actually calculating into this whole thing here. And lastly, the sound intensity equation is pretty simple. Basically, you just take intensity in every direction from the source, and you use that you add them up. And that gives you the overall sound power level. As we said, sound intensity is sound power divided by cross-sectional area. So by simply adding up the sound intensities with respect to the area times the areas, that gives you the power out of that particular section of the source. And you just add those up, and that gives you your sound power. ISO governs these standards. There's a committee that is purely in acoustics. There are other committees that perform other sound power measurements, or rather, they govern the rules and the standards by which sound power is measured for different apparatus. And we'll talk about that a little bit right at the end. But this is the list of sound power standards that everything else is based on. And this is kind of a long list, and you can peruse it a little bit on your own time, but the gist of it is that there's a methodology for performing sound power in anechoic rooms, in reverberant rooms, and then the precision with which you make your measurements is also governed here. So whether you just want a quick survey method, or you want something that's very precise and very accurate, and you want to be able to repeat this over time. You'll be able to repeat all of these over time. However, you will have much more accuracy if you use the precision methods, which, as I said before, those equations take into account the atmospheric conditions. A couple other standards that are involved in sound power measurements are the IEC 60651 sound level meter standards, as well as the IEC 61043 sound intensity standards, and I'll get to those at the end a little bit more. But for the most part, these are the guidelines to performing the methods, and most of the other standards with regards to sound power will be either specific to an apparatus or will outline the type of equipment or the type of analysis you do with it afterward. This is the same list, only kind of organized a little bit better, given a classification, a test environment, and a noise characteristic, and what data you're getting out of it. And again, this is a little bit more. It's more in depth, but it's also easier to read, and it gives you a good idea of the different measurements that you can decipher out of a particular standard. ISO governs these standards. There's a committee that is purely in acoustics. There are other committees that perform other sound power measurements, or rather, they govern the rules and the standards by which sound power is measured for different apparatus, and we'll talk about that a little bit right at the end. But this is the list of sound power standards that everything else is based on. And this is kind of a long list, and you can peruse it a little bit on your own time, but the gist of it is that there's a methodology for performing sound power in anechoic rooms, in reverberant rooms, and then the precision with which you make your measurements is also governed here. So whether you just want a quick survey method, or you want something that's very precise and very accurate, and you want to be able to repeat this over time. You'd be able to repeat all of these over time. However, you will have much more accuracy if you use the precision methods, which, as I said before, those equations take into account the atmospheric conditions. A couple other standards that are involved in sound power measurements are the IEC 60651 sound level meter standards, as well as the IEC 61043 sound intensity standards, and I'll get to those at the end a little bit more. But for the most part, these are the guidelines to performing the methods, and most of the other standards with regards to sound power will be either specific to an apparatus or will outline the type of equipment or the type of analysis you do with it afterward. So the direct method of sound power measurements, I mentioned earlier that we need to be able to measure the environmental parameters. And rather than use a special device like a barometer, the standards actually are pretty slick in that they allow you to use the source under test as a means of determining the room corrections and the environmental parameters. So the direct method, your source basically is your barometer and measurement of speed of sound. Specifically for diffuse field methods, when you're in a reverberant room, the microphones are set up in a parallel pipette or shoebox arrangement because you just want a good distribution of the sound pressure measured over various places in the room. The methods where you perform the measurements in an anechoic room or in a free field, a hemisphere is set up so that you are collecting measurements equidistant from the center of the source. And you see both of these methods outlined. This is the parallel pipette or shoebox method, and this is the hemisphere method. The dimensions of these are Actually, there's no guessing. They're straight up stated in the standards. These are the numbers you pick from. You either have to be twice the largest source dimension, so that means from corner to corner, or 3 times the distance of the acoustic center of the source from the reflecting plane. So if you've got a really tall source, like a machine, that's how much further away, that's how far, you have to be 3 times that distance from the source when you're measuring. The wavelength of the lowest frequency of interest. So that's pretty easy to figure out based on the formulas before. Or 1 meter. So the absolute smallest distance you can be from a source is 1 meter. Basically because that's what's dictated in the standards. It's also the reference distance. So every other calculation measured is either based on 1 meter or 1 square meter of area as your reference. So you can't go below your reference distance for any of these measurements. So the measurement is spatially average sound pressure measurements. We talked about that. But then the next thing you have to measure is your background noise. This is very easily measured by simply leaving the microphones set up where you have them set up for your sound power measurements, leaving your source off, and determining what the background noise of your chamber, your room, or whatever have you, if your shop floor, if you're in an in situ measurement, what that is. You must be at least 10 dB. Your background noise must be 10 dB less than the sound of the source under test. If so, a correction factor may be required unless the source is much louder than your background noise. 20 dB greater than background noise, K1 essentially goes to 0. So there's one more correction factor, the K2 correction factor. And this takes into account the volume of the room, the surface area of the room, and the environmental conditions. So these are those numbers that are hidden either in the C of the equation from before, or the big log S0 times P0 divided by rho C in the other equation for the free field method. And this is just a measurement. In a diffuse field, you essentially measure reverberation time. And this number actually is kind of drops out of the equation a little bit, and you get most of your information from the background measurement in a anechoic room. Since sometimes you can't use your source under test for some reason as a way of determining your room corrections, an additional measurement may be required using a calibrated source. And this then determines the room corrections, and it's called a comparison method of sound power instead of a direct method. It decreases your accuracy just a little bit. However, it allows you to measure sound power of sources that you wouldn't typically be able to in a reverberant room. The room simply the room corrections are the big change here. Comparison sound power can't be done in an anechoic room. It just nor do you really need to. In an anechoic room, your room parameters are pretty straightforward to measure. Measuring sound power with sound intensity is also governed by an ISO standard 9614. One of the really cool things about this measurement method is that you don't have to worry about your environment. The nature of sound intensity is, so we have a source under test in here, the sound intensity is always directed out from the source. So what that means is, in this configuration here, you see this box. As long as I'm measuring the sound intensity here, Any sources that are over here or over here will cancel out, because when I'm measuring this plane, I'll always get a positive intensity from in here, but if I get a negative intensity from over here, it will become positive when I measure this plane. So that's a very cool part of this measurement. The one downside, though, is that you have to make sure that you don't have noises that aren't consistent. So if you have a train go off, or some noise was going on when you were measuring this plane that's different than when you were measuring this plane, then you're going to have some issues, because that'll add some error into your measurements. And again, the measurements are performed with the intensity probe either at a point by point in a parallel pipette arrangement, or you can do a scanning measurement and average the whole thing over one big long measurement. The point by point measurement is more accurate. The nice part about that is also some data that can fall out of that is source localization. So if you have a particular noise source, you can, that a part of the structure or the source that you're interested in the sound of, using the point by point measurement, you can get a source localization. Now, the other part about this is that either measuring each and every one of these dots can be difficult. It can be a pain. And even the scanning method, making sure that you have a consistent scan over the entire source, that's a difficult thing. So what a lot of people do in order to mitigate that is they build fixturing, like a gantry system, similar, like almost like a CNC machine, where they can actually position the intensity probe and take a measurement, and then the software just moves the intensity probe to the next position. Also, local positioning systems. So you've seen a lot of these little positioning systems, like with video game systems, where it'll say, well, this is the orientation of the controller, this is the position in space, I'm collecting that data now. People have been hacking, for lack of a better term, these positioning systems in order to be able to take these measurements more accurately. So I said before that there are sound power standards with respect to specific pieces of equipment, and this is very much a short list. There are dozens of these standards out here. The majority of these specific ones, as you see, are governed by the Acoustics Committee, by ISO. So you see lawnmowers, two-wheeled mopeds, ducted silencers for HVAC, computer and business equipment, and then IT equipment. These two overlap a little bit in some areas. But these actually are governed straight up by the ISO Acoustics Committee. These were written by people who are acousticians, and they know what they're looking for when it comes to sound power measurements. But sometimes you have other groups, other standards groups, that they know they should be measuring sound, and so they take it upon themselves to perform the measurements. Because of that, you have this list of standards here, which are sound power standards that are written by non-acoustic committees in ISO. The first one is tractors and machinery for agriculture and forestry. As you can imagine, people working on this equipment are going to be exposed to certain amounts of noise, and that all needs to be reduced, hopefully over time, or at least held to a certain threshold. Machine tools, noise of machine tools, lathes, mills, any type of machine that you might see in a machine shop. Welders, they emit some noise. Photography, and this is mostly for the sound power. This standard here in particular is for the sound power of a projector. You don't think about it when we're in a theater, but the projector is actually making noise. And over the years, we have made it so that we can reduce the noise output by the projector so that the audience inside the theater doesn't hear it. Gears. Yes, there's an ISO committee for gears, just like there's an ISO committee for screw threads and bolt threads and the like. But this is important because gears mesh, and that mesh makes noise. So there's an acceptance code for gearboxes and testing the airborne sound generated by gears. And then lastly, there's internal combustion engines, which includes the engine with and without the muffler system or the exhaust system. And all of these things need to be measured. That is the end of the Sound Power Basics presentation. This is the end of part 2. I hope you enjoyed listening, and if you have any questions, please feel free to contact PCB Piezotronics. Thanks. Bye-bye.